Hey there, calculus fans. Making another video about derivative rules. This is the proof of the chain rule. Um, Again, this video is made primarily for my business math class, so I'm going to teach it at a fairly basic level. I'm not going to go into details of differentiability and other things that you would study. If you're interested in those things, take a course on real analysis. That's typically where you would study more in depth. How do we prove these things? What are counterexamples? Math is all about those ideas of how do we prove it, or can we find one example where it's not true? But anyways, back to this again. The definition of the derivative as we've defined it. Watch my previous video about how I use the definition of derivative to prove the product rule. It starts like this. So you have some function. Let's use some letter other than f. Let's use L this time. It doesn't matter. So L minus L of x. L for Loveless, I guess. Is this. I talked about this in the last video. You have this some point x, some second point, which we like to call x plus h, just for simplicity of the limit. But you could also call it a and b as the 2 points. Okay, so this is this slope, because this point is what you get when you plug x into the function. This point is what you get when you plug x plus h in the function. And if you do rise over run, you get this. This is the slope of the so-called secant line. We would like to know what happens when h gets closer to 0. So whenever we encounter a new situation, we apply this rule. So I'm going to give an example first. So imagine we have two functions. One function I'm going to call f of t, and it's going to be t cubed. Now we've learned how to do the derivative of that. We've learned that the derivative is 3t squared. Okay, now we have another function, g of x, and I'm going to have g of x be x squared. I'm going to do this. This is this example I visualized over here. I'm trying to do all of this with a visual example because I think that makes it more fun. So here's this other function, in g prime of x is 2x. So those are the derivative we have known. A composition is when you put two functions together. So f of g of x, which is very important. This is the most important derivative rule by far. I guess I'm stating an opinion, but and this is saying you are doing two different operations. This is a very general thing about what to do here. How do we combine all these facts correctly to get the slope? Okay, and I've drawn it over here. I chose kind of an interesting graph. Here it is. You can see the slope is negative. This is the slope of the slope of the derivative. So let me show you right here. The slope is 0, and you can see that. The slope is 0 here. And then the slope is negative again. And then we get to the bottom, which is right here, and the slope is 0 again. So here the height is like negative, I guess we could calculate it, negative 64. The slope is 0. And then the slope is positive. And then there's a moment when the slope is 0 again, and then it goes back up. We call these a horizontal point of inflection, a minimum, another horizontal point of inflection. I personally call these a chair, because it looks like someone could sit there. A chair facing to the right, a chair facing to the left. Okay, anyways, the question is, what's the derivative? And the chain rule says the following, and then we'll talk about proving it. The chain rule says if you have a composition like this, one function inside of another, it's different than a product, and you want to take the derivative. That's what this symbol is. You take the derivative of the outside function, and then the important piece of the chain rule is this: you leave the inside alone. And I think of that as the first step or the first link in the chain. Then you put a little multiplication symbol. So basically we're saying the derivative at whatever value you get from g times the derivative of g at x. So it's something you'll get very comfortable with, but it's the product of their rates. There are all sorts of different proofs and explanations for this, but I think what we should be doing is going directly to the definition. But let's first use this. So if I want to take the derivative of this, here's what we do. You can think of this in a number of different ways. I'll give two explanations here real quick. One is you could cover it up. Put your thumb over this and just ask yourself, what is the derivative of something cubed? Well, it's 3 squared. That's the chain rule. It says ignore everything on the inside and just take the derivative of the outside. And then the next part of the chain rule is then you copy down the inside, whatever it was, which it was this, and then you put a little dot for multiplication and you restart the process, but without the cube. And then whatever you put here is going to be the derivative of that, which in this case is 2x minus 0, or just 2x. And people who take calculus, that needs to become routine because we're going to do it so much. So there you go. That's the derivative. Sometimes you have more functions inside. It's not that bad. It becomes, like I said, really routine. If you want another explanation that I sometimes give to students, here we go. Another explanation is you walk up to the function from the left, and what's the first thing you encounter? The first thing you encounter, so we're going to go for a little walk. We're going to walk this way. The first thing we encounter is this symbol. This symbol goes with this symbol, which is all associated with the cube. So then you take the derivative of the cube, which we did, 3 squared. Then you erase that piece, and you copy that down, and then take the derivative. That's just another way to say the same thing. I just like to say it twice to emphasize. That's the formula here that I graphed. And you can see it is the slope. If you wanted to know when it was 0, it's 0 at -2, +2, and 0, which tells me where the bumps are. Now, these technically aren't bumps. They're places where the slope is 0 for just an instant. They're horizontal points of inflection. But there you go. Cool. I thought that was kind of a cool little picture. Okay, so now to the proof. Let's get rid of all this, get rid of our example. That does work. It's really the essential derivative rule. I can't say that enough. Okay, so now let's try to use the definition. So instead of L, I'm going to use f of g of x. And I should note that there is a weird symbol for composition, a little circle. And that's just there's no value in me telling you that. It's just, I'm worried you'll go somewhere else and see that. Okay, so that's what that means. All right, so what we would like to do is to figure out what f of g of x plus h minus f of g of x over h. And we'd like to understand if there's anything we can say about that as h goes to 0. And so it's a similar clever trick. I assume that whoever first observed this observed the fact first on lots of examples and was like, okay, I know what I need to prove. I need to make the derivative of g appear. So if you were someone that had to prove this yourself, and you were trying to do this, let's enlarge this. You were trying to do this yourself, and I have some of my notes down there at the bottom. I just wanted to show you them in a moment. But you might say, I am expecting the derivative of g to make an appearance based off of the examples I've done. And the derivative of the g looks like this. Based off of this idea, you could say, well, how could I change the look of this without changing the value? So the clever idea is to multiply the top and bottom by this. And again, I think things like this, I didn't get to speak to I'm pretty old, but I didn't get to speak to Newton when he derived these. But I imagine this is how it works. You do a lot of examples. Oh, I see what this is. How do we prove it? Okay, we need to make this thing appear. So they multiplied by 1 in a clever way. There's subtleties to talk about, but I'm going to leave that for when you take real analysis. Okay, so then the proof is to rearrange the fractions. So you're going to say f of g of x plus h minus f of g of x. And I'm just going to rearrange. It's like I'm going to write 2 times 7 over 3. And I'm going to instead write it as 2 over 5 and 7 over 3. Nothing really fancy here. So I'm going to swap the location of these two items. And so it's going to be g of x plus h minus g of x times g of x plus h minus g of x. I didn't say the proof would be exciting. I just said I was going to show you what it generally looks like. We have done it. We have made, this is going, as h goes to 0, and again, in my class that I'm teaching, we don't do limits. It's an introduction. We just talk about it. And so I'm trying to prove it in this very generic way, but I feel bad if I skip this completely. So as h goes to 0, this is going to approach g prime of x. And we know that that's part of what we're trying to prove. So then we come back and look at this, and that really doesn't look that familiar. So it's a clever little idea. Let's call it t. I'm going to label the bottom t to try to just help you see something that I'm seeing. Okay, so let's make the bottom of this thing just t. And I'm not actually doing anything, I'm just reordering it to make it look more familiar. Okay, and I have negative f of g of x. Okay. And what can I say about this other thing? Well, this other thing right here is equal to g of x. I haven't done this for a long time. It's kind of fun to... This is all stuff you do in a real analysis course. Graduate school. Eventually you get to a place where something like this isn't really scary. I know we're pushing a lot of symbols, but it's not as bad as it looks. Okay, so what have I done? I've just rearranged it, but that kind of looks familiar. That looks a lot like a derivative. You may say, well, it's not the exact same symbols, and you would be true. You don't have to have x's and h's. You could have other symbols. So let me rewrite something for you and say, what if I told you that you had, let's say this first, f of x plus h minus f of x over h, and you let h go to 0, you're going to get f prime of x. Okay, now I'd like you to free your mind from the variable x and h and change the h first to a t. As t goes to 0, that's also going to be the same. So it doesn't matter that it's an H or a T or a W or a Q or something that looks like a piece of broccoli. It doesn't matter. Sometimes I do. I'm going to plug in broccoli when I want to emphasize something is it doesn't matter, the location. Okay, now I'm going to do one other thing. I'm going to get rid of this X. We're going to say, for the moment, I don't like the letter X, and I'm going to make it the letter U. I don't know why I like the letter U. That's still the derivative. Now, I want you to think about this for a second. If I had called this U, and I had called this U, then what we're looking at is exactly this. And as t goes to 0, now there's a comment to be made here, which is we don't know that t is going to 0. We know that we're making h go to 0. That's the goal in this problem. But as h goes to 0, this is going to approach g of x minus g of x. And as long as our function doesn't have a big break in it, as long as our function is continuous, this is the subtleties you have to talk about if you want to prove it more formally. But if I'm just proving it to just giving a plausible argument for most situations, I have some more freedom. Okay, so this is going to 0. T is going to 0. And if t is going to 0, this thing is approaching f prime of u. So the answer is the product of these two things. But that's not u. It's whatever g of x is. Aha, there's our rule. So I don't know if that's enlightening. Take a class in this, but and that's what you see in my proof here. Oh, I called it H1. Oh, that would have been nicer than T. I don't know that really matters. But at this point, you should just practice, and maybe that's for a separate video. I can do a bunch of them. But you just have to recognize when you have a function inside of another function, x to the 4th to the 10th, the derivative is fairly quick to do. You just do the derivative of the outside, which is 10. Why is that showing up? Okay. To the 9th. You say, ooh, I'm tired from that. And then you say, okay, he said, copy down whatever it was. Okay, I got it. Dot. Erase the outside, so to speak. And then do the derivative of the inside. 2x. And then a few nice things about this rule. You can inspect that you've done it correctly. I mean, you can just look at it and see, did I take the derivative of the 10th power? Yep. Did I take the derivative of the inside? And is it out here? Yep. Okay. Any course you take in calculus, you're going to do a lot of practice on that, and you're going to get good at it, but I wanted to give you a little feel for how someone goes about proving such a thing. Hope you found that interesting.